Our next speaker is Professor Qiu Yu from Tsinghua University. The title is Moduli Basis of Quadratic Differentials. Let's welcome.
So it's my great pleasure to give a talk here. So this talk is based on this archive. And yeah, it's well about the moduli space of quadratic differentials. So first, let me mention some motivation. Yeah, since I assigned to this algebraic geometry session, so we have some motivation from this area. So in particular, it's mirror symmetry. So originally, this predicts that two geometry give the same physics. So on A side, you have symplectic geometry. You have, say, Abel threefold X, and on B side, you have complex geometry. You have a mirror threefold X check. And somehow, when you look at this pair of mirror manifold, you can obtain some numerical or other kind of equivalence. So this is from physics point of view. So from mathematical point of view, you can make things more precise. So I will mention most famous two approach. The first one is SYZ's conjecture, which basically says mirror symmetry is T-duality, meaning that you can construct this mirror manifold via special Lagrangian torus fibration. So basically means that you have a common base B, and for non-singular fibers over this pair, they have dual torus. For me, originally I'm doing more categorical stuff, so I'm more familiar with this approach due to Kontsevich, which says that from A side you can construct this derived Fukaya category. On B side you can construct a bounded derived category of coherent sheaves, and these two categories are equivalent. So you can view this equivalence as triangulated category or A infinity category or something similar. So a conjectural picture in this area is that from these two manifold, you can cook up the same moduli space. So on one side, you have space of stability condition, and on the other side, you have some scalar moduli. Yeah, but this is a big conjecture and very hard to approach, say, in the Abel threefold case. But we will mention some developments in this direction. So this is close related to many theories like Donaldson-Thomas theory, cluster theory, and more. So this stability condition is a mathematical interpretation of pi stability in string theory. And actually, for example, in Professor Sun's talk, he mentioned this stability, which is given by the degree and rank. So that's a canonical stability condition, which is a point in the space of stability condition. So here is the outline of my talk. So as I mentioned, in general, the development is slow, but in the Riemann surface case, we have correspondence between stability condition and quadratic differential. So this is basically what we mean the scalar moduli in the reduced case. And then I will mention two results on categorification of compactification. So yeah, so these two is two results or two family of results is kind of to make the bridge between categories and dynamical system. It's kind of the frame type of works. And for the last part, I will mention that using the categorification in dynamical system, we can prove some results in moduli spaces, in particular this monodromy conjecture, where the big picture is that we want to prove some K-1 conjecture, but that's still in progress in general case. Yeah, so first let me tell you about quadratic differential as stability conditions. So for the moduli space of quadratic differential, we usually denote it by this quad with some numerical data. So a point in this moduli space consists of a quadratic differential on a Riemann surface, and we fix the genus G. And then you need to tell me the singularity type of this differential, which is given by a collection of numbers. So we will usually divide it into two families. The first is finite type singularity or critical points, which consists of simple pole and zeros. Here we also allow the marked point with just regular point. So if you only have this finite critical point, then it's homomorphic. But in our case, we are more interested in the case that is meromorphic. So you have double pole or higher order pole. And locally, you can express this differential in a form like that. So usually here you can plug in a polynomial, for example, and you just take the dz tensor square. So it's a section of the cotangent bundle tensor square. So you can also regard this a point here is a algebraic curve with a divisor given by this data. So that's the connection to algebraic geometry, although usually I will not take that point of view. So for example, if you take G to be 0, so the Riemann surface is CP1, it's possible to write this moduli space globally by just say you give me this polynomial, say without double 0, so the discriminant is non-vanishing, and then all polynomial with dz tensor square of this form will give you a quadratic differential on CP1, and it is in this stratum of this moduli space, so it will have n+1 different simple zeros, so we will write something like that. And at infinity, if you change the coordinates, you will see the order of the pole at infinity is n+5. Yeah. So in genus 0, basically this space is more or less the moduli space of say degree a fixed degree polynomial with non-vanishing discriminant. And the most important structure of quadratic differential is the foliation structure. In fact, the quadratic differential on Riemann surface is equivalent to measured foliation. But here we only draw the foliation. So what is that? So on C, you can have the canonical or trivial quadratic differential just given by dz tensor square. Then if you solve the equation, the imaginary part of z equals 0, this equation will give you a family of horizontal parallel lines. So this is the canonical foliation on C. And using the quadratic differential, you can pull back this structure to your Riemann surface. And basically, there are 3 categories of foliation you can have. So for finite singularity, so here is the simple pole, here is a regular point, here is a simple 0. So for finite singularity critical point, you are basically gluing many copies of upper half plane at 0 along the axis. So the number of upper half planes equals the order of your singularity plus 2, because it's quadratic, so you plus 2. So this is one type of phenomena. And for double pole, the behavior is a little bit strange. You can have many circles at the same center. You can have many lines through this point, or you have a logarithm spiral. And for higher order pole, then you take the number of pole -2 copy of plane gluing at infinity. So here you are gluing at zeros. So that's why it's called finite singularity, because when you go there, the distance is kind of finite. But for pole, is you are gluing infinity, many copies of above plane locally. And so there were a couple of special directions in both cases. So because later we will study the topology of this moduli space, so we want to turn the numerical data into topological ones. And then, yeah, let's just call this DMS. So, so the genus G give you a topological surface, and for finite singularity, we will turn this into a set of decorations on this topological surface. And the order of the singularity will be given by the weight function. And for double pole, because its behavior is very strange, so we will just call this punctures. And for higher order pole, we will replace each pole with a boundary component. So basically doing a real blow up. And the order of the pole will record it by marking the marking points on this boundary component. And the number of markings equals the order of pole -2. So basically, here, for example, when you have a pole of order 5, you have 3 distinguished directions. So we will replace this pole with a boundary component and 3 marked points indicating 3 directions to this pole. Yeah, so this is the topological version of the numerical data for a moduli space. So for example, if you have genus 0 and you have 3 simple 0 and order 7 pole, then the topological surface you draw is a pentagon. So this 5 points correspond to the 7 minus 2. So that's the order 7 pole at infinity, say. And you need to draw 3 decorations inside in red here. And their weights are all 1, so I didn't label the weights. And on this side, you can have a diagonal, which indicates you have an order 4 pole, and you can say have 2 double pole and 4 simple 0. So the sum of all the data equals 4G minus 4 by Riemann-Hurwitz formula. Yeah. And let's look at this simple case. When on CP1, when you have 3 simple 0, 1 order 7 pole, so typically you will have a quadratic differential globally written as this. And the foliation structure is looked at like this. So this is the foliation around the infinity, and on this pentagon with 3 zeros at a generic point, meaning you don't have set of connection, the foliation always look like that up to symmetry of the pentagon. So you see that if you take the homotopy class of generic trajectory, meaning connecting poles, you will get a triangulation of the pentagon, which is called the WKB triangulation. And in this case, each triangle will be once decorated with a simple 0. And in general, when you have a quadratic differential without saddle connections, on this decorated marked surface, it will always have a mixed angulation, so divided by many polygons. And for each polygon inside, you will have a 0, and the order of the 0 equals the number of edges of the polygon inside minus 2. So in many cases, we will only consider simple zeros and then it will always be triangulation. And this triangulation, these three, later we'll see it corresponding to the Calabi-Yau dimension in the categorification. Okay, so we want to do some categorification in dynamical system, and so here is a correspondence from Fukaya category point of view. So when you have a Riemann surface, we want to have a triangulated category. Usually you can take the, say, topological Fukaya category or a general Fukaya category, but you need to take a subcategory maybe, and or Fukaya-type of category. And the point is that the curves or arcs on this surface will correspond to objects. So for example, if you take topological Fukaya category, the symplectic structure basically vanishing, and the Lagrangian submanifold just becomes one-dimensional manifold of this Riemann surface, so it's just curve and arcs. And then the intersection corresponds to Floer homology in Fukaya story, or just homomorphisms in the category. Yeah, and next I will tell you what is the quadratic differential correspond to. So although we are calling this Fukaya-type category, I didn't use any symplectic geometry. Although, I mean, many things you can find symplectic origin, but I'm doing things more algebraically. Yeah, so as I mentioned, the things we were using is stability condition on triangulated category. So a stability condition on a triangulated category consists of two data. The first is called central charge, which is a group homomorphism from the quaternion group to C. The other is slicing, which is an R collection of T structures, and they satisfy compatible condition. So for this R collection of T structures, sometimes you can replace this with just a single T structure, because the other ones can determine by the central charge. So for example, in algebraic geometry, in Professor Sun's talk, you will take just one T structure with canonical heart to be the coherent sheaves on a variety, and that's correspond to a canonical T structure in the bounded Dirac category of coherent sheaves. And then the central charge you are taking is the degree of an object plus the rank times imaginary number I. So that will give you a central charge. But that's just one stability condition. But from our point of view, we want to take all stability condition on a triangulated category D, and then Bridgeline shows that this forms a complex manifold, and the local coordinates is given by the central charge. So instead of looking at one stability condition, you look at all the stability conditions, and this is kind of a moduli space stuff. So the one of the seminal work in this direction is given by Brian Smith. They show that if you give me a stratum of moduli space of quadratic differential, so here for simplicity we will exclude double pole. I mean, later we will mention what happens in the double pole. So say without double pole, then you can take a 3 Calabi-Yau category, which can be constructed from quivers with potential associated with triangulation of this marked surface. In fact, Ivan Smith shows that this is actually a subcategory of some derived Fukaya category of genuine symplectic threefold, and this is just generated by some Lagrangian sphere. So what they show is that this moduli space of quadratic differential can be identified with a kinetic component or principal component of the space of stability condition quotient out autosymmetry. Yeah, because when you consider moduli space, usually you want to take out all the symmetries. Yeah, so basically this result tells you that so instead of looking at moduli space of quadratic differential from, say, flat surface point of view or algebraic geometry point of view, you can just use homological tools in algebra and category to study everything. And at a similar time, so actually this appears in 2013, this appears in 2014, although they published in the same year. Haydn, Kazakov, and Kazevich give another version, is that for any stratum of moduli space of quadratic differential, they construct this topological Fukaya category. And then they show any stratum of moduli space of quadratic differential can be categorified by this category. So this topological Fukaya category is much easier than the 3-Abel category because it doesn't involve any symplectic geometry in some sense. And the approach is a little bit different. Yeah, so here the category is more complicated. So you do not have a full description of objects and homes for this triangulated category. But here, actually, you can describe the category, basically all the information from the surface. Yeah, but anyway, the key point in these two proofs, I mean, although the proof is a little bit different, but the key point is that you want to identify the first homology of this decorated marked surface with the quadratic group of the category. So these are both lattice of rank m, for example. And then the central charge, which is the local coordinate in the space of stability condition, becomes the period map in the moduli space of quadratic differential. Yeah. So the period map is basically here you have the quadratic differential. So this integral means that you need to take a square root of the quadratic differential to get an abelian differential on the spectral cover of the Riemann surface. And then you can integrate there. So now we can extend the correspondence between category and the dynamical system as follows. So quadratic differential becomes stability condition. So as I mentioned, that homology group corresponds to quadratic group, period map becomes central charge, and more. For example, on stability condition, as mentioned in Professor Sun's talk, people will care about the stable objects. And this will actually correspond to saddle trajectory in dynamical system. And in general, an object in the category will have atrium filtration. Basically, stable objects are kind of the fundamental blocks to build up other objects. And on flat surface, the saddle trajectory are the basic geodesics. And if you want to connect or realize other curves, then you can use this saddle trajectory to make a broken geodesic to get a homotopy class of other curves. Yeah, so basically, once you have this correspondence, you can have a dictionary in these two areas to understand each other. So let me mention this result is that we have a uniform approach together with Merlin-Kreis and Fabian Haydn that originally when BS and HKK proved the result, they are looking at one category and want to calculate the step by finding the moduli space of quadratic differential. But now in this work, we are doing the reverse direction, is that we construct infinitely many Fukaya-type of category to realize the same stratum of moduli space. And in fact, we can make this category Calabi-L n if n can divide the order of zeros. Well, actually, it should be order of zeros plus 2. Yeah. The approach here is using pervert-Schober's. Yeah. So let me mention some compactification results. So compactification is important in algebraic geometry and flat surface. There are two classical approach due to Deligne-Manford and Thurston. Yeah, but I'm not an expert here. But I will only mention that recently there's a generalization of Deligne-Manford's compactification due to BCGGM. Basically, they got a smooth compactification, which seems better than the Deligne-Manford's ones. So I just want to show that there's an ongoing project to categorify this compactification. So to understand this compactification, the point is that if you start with some stratum with this topological data, so a diagonal surface, you want to do compactification, then you want to add some boundary stratum to this stratum associated with this surface. Then what kind of boundary strata you want to add is that you can shrink some of the subsurface. And the shrinking meaning that you will replace, you will get rid of this subsurface, and for its boundary component becomes some finite singularity or decoration with weights in your collapsed subsurface. And then for this collapsed subsurface, you take the stratum there and add to the boundary of your compactification. And together with Barbier, Muller, and So, we first give a categorification of collapsed subsurface, and it's very easy in the triangulated setting. It's just by the vertical quotient. So basically, you have a Schrödinger sequence. So when you have a subsurface embedded in the big surface, the corresponding category can be embedded, and you take the quotient. And in fact, this quotient category, you take the space of stability condition there, it will categorify the boundary stratum. And my collaborators also use this result to categorify this BCGGM compactification in type A case. Because in type A case, basically, there's no closed geodesic, and everything is very easy. But in general, we're still working on the full generality here. Yeah, so this result just to show off some correspondence between category and the dynamical system. As I mentioned before, when you have kind of this type of correspondence, you can build up more things in the dictionary. But I'm more interested in another compactification, which appears in the Bridger and Smith work that I omitted a minute ago. So the categorification above is that when you add boundary stratum, you use a new category to categorify this boundary stratum. But in fact, in the other part of Bridger and Smith's work, what they consider is that when there are double poles, they want to allow the collision of double pole and a simple zero. So this is a special case of collapsed subsurface. So here, basically, you are taking a disk containing a double zero and a simple pole, and collapse these two, this disk. And equivalently, you just allow the collision of these two type of singularity. And then instead of realize this boundary stratum, we take the union of the boundary stratum into the main part. And for technical reason, you also need to do some orbifolding. Yeah, but in Bridger and Smith's work, when you have this double pole, they need to allow this collision, and they can categorify a partial compactification with orbifolding of the stratum here. And the reason to do this is that on the other side, the three Calabi-Yau category is natural from the point of view of cluster algebra theory. So that's why they prove this type of result. So in my work with Fabian and Merlin, we can categorify this single stratum directly. So a natural question is that what is the relation between these two? I mean, from the moduli space side, we know is a partial compactification with orbifolding. And in my new archive, what we do is that I want to tell you that the relation is given by a family of 3 Abel category. So the partial compactification is given by a deformation of 3 Abel category. So this deformation corresponds to a partition of the set of double pole divided into, I use this yin-yang because there's a Z2 symmetry. So for Chinese and also foreigner, you see yin-yang, you know there's a Z2 symmetry. I don't need to explain, right? So the point is that for this family of deformed 3 Abel category, we can realize the partial compactification one step by another. This specialized to the 2 cases I mentioned before. Yeah, so now next, the reason I want to show this result is that next I want to show some application of this categorification. So up to here, we're still just say we can construct this moduli space using categorical tools. But can we use this correspondence to prove something about the moduli space that people cannot do previously? So this is about the topology of moduli spaces. So let me first mention the classical K-1 conjecture. So the bread group is that if you give me a thinking or Euclidean diagram, or in general any diagram, and there's a bread group or artin bread group. Basically, for each vertices, you have a generator. For each pair of vertices, you look at the edges between them. And if there's no edge, you will have a commutative relation. If there's one edge with label 3, or sometimes people will just omit this 3, so typically you will have a braid relation. And in general, you can have higher braid relation. So if you are not familiar with braid group, by adding square to 1 relation, you get the Y group. So maybe that's more familiar. And the thinking classification, meaning that the Y group is finite if and only if the diagram is a thinking, Coxeter thinking diagram. And the braid group is a natural covering of the Y group. And then if you take the corresponding complex space, which is the Cartan subalgebra of the corresponding type, you delete some hyperplanes, which is the regular part of the Cartan subalgebra, you get this hyperplane arrangements. It is well known that the Y group will act faithfully on this regular part, and the pi1 of this space hyperplane arrangements equals the braid group. So for example, if you in type AN, this regular part of Cartan subalgebra also corresponds to polynomials, and the hyperplane you take out is correspond to the polynomial with multiple 0. So precise the things appear before. And in fact, if you take out the braid group, so this part, and you need to further take out some cyclic group, you will get the moduli space we mentioned in the first slides of quadratic differential. So that's the link. Basically, this is only because that moduli space of quadratic differential is more or less the space of polynomials. So the classical K-1 conjecture asserts that the universal cover of these hyperplane arrangements is contractible. So basically, the pi1 of this space controls the homotopy type of it. Yeah. Deligne proved this conjecture in the finite case. This finite meaning the Y group or the Coxeter group is finite many years ago. But even in the Euclidean case, it's only a recent breakthrough in the Euclidean case. Yeah, so it's not very easy. But I'm more interested in variation of this conjecture. So the first variation is conjectured by Kontsevich and Zorich. And they say that the stratum of moduli spaces of quadratic differential should be K pi1, where the pi 1 is some subgroup of mapping class group, something like that. So so this conjecture may be too general, so maybe you need to add some condition, like maybe you need to have enough many simple zeros, or the most of the zero have the same order, or something like that. Maybe in general this is not true, but for generic case, I hope this is true. So this is one variation of the K-pi1 conjecture. The other one is that for space of stability condition, people conjecture that the connected components of it is contractible. This is already proved in many interesting cases, not so many. Yeah, but this is also very hard. But by the correspondence we mentioned before, basically, and also some other work, the categorical version should be the strongest. It can imply the geometric ones. And people expect that the kinetic component of space of stability condition is the universal cover of stratum of moduli space of quadratic differential. So this is on this side. And due to a result of Bridgeland, the categorical version also can imply the classical version. So that's kind of the big question I'm very interested in. So some progress in this direction. So for finite type, together with John Wolf, we show that the space of any connected component of space of stability condition is contractible. And the finiteness condition is, you can think that this is the finiteness condition correspond to the finiteness of the Y group. And indeed, if you plug in a result of Bridgeland, our result can imply the first, our result implies the categorical K-pi1 conjecture in ADE case, and then implies the classical K-pi1 conjecture, so the Linz result. But we have a new proof for ADE case. And together with Xiaoting Zhang, we also can handle the BC, FG, HI case. So the point here is that you just need to construct some category so that the space of stability condition can be realized as the universal cover of the hyperplane arrangements. Then you can plug in this general result to prove the classical K-pi1 conjecture. So in the Euclidean case, we're still working on a proof. I mean, although Paroni and Savati have a proof, but for example, in the exceptional type, they depend on some calculations by the computer. And also, the point is that to have a categorical proof, the application will be many more cases and more fundamental in some sense. Yeah, but let's return to the topology of moduli spaces. So initiated by Kontsevich and Zorich, they classify connected components of moduli space of abelian differential. And in this direction, there are many works to classify kinetic components of moduli spaces of K differentials. So not just abelian, quadratic, people can handle K differentials. But for higher homotopy groups is much harder, even for pi1. So, and in some sense, I mean, pi1 maybe is non-trivial, right? And the higher homotopy groups, we hope they vanish. So in this direction, to understand the pi1, let me first mention a little bit about the mapping class group. Because in Kontsevich and Zorich's conjecture, the pi1 of stratum of moduli spaces should be some subgroup of mapping class group. In fact, a generalization of a braid group in low-dimensional topology is this surface braid group, which is pi1 of the configuration space of this surface, regarding this kind of decoration as configuration. And typically for this group, you have two type of generator. So you can change or switch this two decoration or two zeros around to get a braid twist. This is also called the half Dan twist, because if you take the branch double cover of this picture, branching at these 2 points, this will become the Dan twist. And the other thing is that if you have just one zero or one decoration, you can push this around to get a diffeomorphism, which we will call L twist. Yeah, I will mention these two as monodromy towards the end. So basically, we need to understand this type of things. They are the generator for surface braid group. So previously, I introduced this subgroup of braid twist group of mapping cast group. Basically, for surface braid group, you have two types of generator. And I say if there's no double pole, you only need to look at the braid twist to generate a subgroup. And this group is isomorphic to the spherical twist group of the corresponding 3-carbon category. And using this group, together with Alistair, we calculate the fundamental group of the stratum of moduli space of quadratic differential with simple zero, no double pole. And this is precisely the braid twist group. And you also need to have the symmetry of the surface without the zero. And we saw, also we can show that the space of symmetric condition is actually the universal cover of this stratum. So this is the previous result. And in my new preprint, I basically generalized this result to the double pole case. And more is true. So I also calculated this moduli space. Notice that this can be a single stratum, or you can do a partial compactification. So unify some stratum, allowing collision of double zero and simple double pole and simple zero. And the fundamental group is essentially the braid twist, but you need to add a little more things. But more interestingly, this is actually the kernel of Abel-Jacobi map. So the classical Abel-Jacobi map is the one in algebraic geometry. You map to the Jacobians. But here we consider the topological version, where basically when you take a braid twist or L twist in the mapping cast group, you look at how the zero goes, and you get a class in the first homology of the surface, forgetting about the decoration or the zeros. And you take the kernel of this, and this is precisely the fundamental group of this quadratic differential. So this map is considered by Walker and others before. And the reason we want to consider this strange partial compactification is because when we do this, this fundamental group or the main part of it can realize all non-exceptional Artin braid group in the Dinking or Euclidean case. So in particular, with this result, if we can prove the geometrical K-pi1, and some special case can imply classical K-pi1 for all the non-exceptional case. But here we actually get many more examples. So actually, this type of the kernel of AJ map is this result is also known as the monodromy conjecture because of the following reason. The braid twist I mentioned before, topologically, you can also geometrically realize as this picture. So basically, previously we only have the zeros going around, but you can draw all the foliations and look at how this realized in the moduli space of quadratic differential. And the reason there's a loop here is that these two zeros can collide into a double zero, but this point of a quadratic differential with double zero is not in the stratum in your moduli space, and therefore you have a generating loop, and this is the monodromy in the moduli space. And similarly, the L twist that I mentioned before corresponds to this picture, and the missing point in the stratum is the collision of a double zero and a double pole and a simple zero. So basically, this is why we can allow some of the collision, basically meaning killing some of this type of loops. Yeah, so that's why that's essentially what we're saying is that these two monodromy, you can forget about the foliation structure and look at the topological structure, and you still get the fundamental group of modular space. So I will finish here.